Hello everyone and welcome. From now, over the next few lectures, we are going to cover Laplace domain analysis of dynamic systems. And why are we doing this? We are doing this because no matter what technique you use, whether you do empirical modeling or you do first principles modeling, ultimately one ends up with, after linearization and things like that, the most basic dynamic elements that you end up with are linear time invariant ordinary differential equations, and these differential equations can get larger and larger in terms of their order. We've looked at first order, second order, but you could have 10th order, you know. And Laplace domain analysis then gives us a very simple technique for analyzing these systems from the point of view of control. It also allows us to easily solve these linear time invariant ordinary differential equations and also look at the characteristics of the solutions in terms of whether the solution is going to be stable, whether it's going to be oscillatory or not, and things like that. So the next few lectures are going to be about Laplace domain analysis. In this lecture we are going to cover Laplace transforms. I'm going to introduce Laplace transforms to you. So what is a Laplace transform? Well, Laplace transform is a function. Laplace transform is a transformation that transforms a function in the time domain to its corresponding entity in the Laplace domain or the S domain. So it transforms a function from the time domain to the Laplace domain. And why do we do this? We'll get that later, but by definition, the Laplace transform of a function f in time, is by definition integral from 0 to infinity f of t e to the power minus st dt. And by the way, this strictly speaking, it's the limits are minus infinity to infinity, but in control systems we usually have causal systems, and also the system is at rest at the initial condition, so everything is 0 t less than 0. For time before 0 units, everything is 0 anyways. So therefore you get the one-sided Laplace transform definition as noted here. So that's the definition of the Laplace transform. So it transforms, you can see, once you integrate over time and take the limits time going from 0 to infinity, you are left with a function in S, and that is the Laplace transform of the function ft. Why do we do this? Why do we do Laplace transforms? It's because it converts a linear time invariant ODE in the time domain into an algebraic equation in the S domain, and we all are very comfortable manipulating algebraic equations. So instead of manipulating large ordinary differential equations, d dt, d to the power, second derivative, third derivative, nth derivative, it's much easier to algebraically manipulate the S domain algebraic equation. That is why we do Laplace transforms. ये क्या हो रहा है यार? So now we'll cover Laplace transforms of some common functions. Let's see, what are we going to look at? We're going to look at the unit step. What is the unit step? U is equal to 1 for time t greater than 0 is equal to 0 otherwise. Actually greater than equal to, let's say, okay, at time t equal to 0 it goes to 1. So if we want the Laplace transform of this guy, by definition the Laplace transform is going to be integral 0 to infinity 1 times e to the power minus st dt, and the integral is going to be e to the power minus s of t divided by minus s, and the limits are 0 to infinity. At infinity, e to the power minus st for s less than for s greater than 0 goes to 0, and as t goes to 0, e to the power minus st goes to 1, and so this is equal to 1 by s. Okay, so now let's look at a unit ramp. Unit ramp would be 0 to infinity t times e to the power minus st dt. So the unit ramp is this guy. This is time t equal to 0. And if I integrate this guy, how do we integrate it? I guess we integrate by parts. Yeah. Okay. So t times e to the power minus integration by parts. First function, second function, divided by minus s minus integral of derivative of t, which is 1, times integral of that guy, and that guy becomes e to the power minus st divided by s dt, and of course the limits are 0 to infinity. Here the limits are 0 to infinity, and therefore what you get at t equal to 0, at t equal to infinity, e to the power minus st goes to 0 much faster than t, so this guy will be 0. At t equal to 0, t is 0, so this goes to 0, and over here we get minus e to the power minus st divided by s square. Limits are from 0 to infinity, and this will turn out to be 1 by s square. Yeah. So we looked at a unit ramp. Now let's look at Laplace transform of e to the power minus at. So this Laplace transform is going to be integral e to the power minus at times e to the power minus st dt, 0 to infinity, and this is going to be integral of e to the power minus s plus a t dt, and this is going to be divided by limits are 0 to infinity, and so this guy turns out to be t equal to infinity, the term goes to 0, t equal to 0, term goes to 1, minus minus, so it will be 1 over s plus a. Another one that we may like to look at is Laplace transform of, and this guy is going to be integral of t e to the power minus at e to the power minus st dt, 0 to infinity, and this guy is going to be integral t e to the power minus s plus a dt. Integrate by parts. This is the first function, this is the second function, so that's going to be t e to the power minus s plus a t divided by s plus a with a negative sign minus derivative of t is 1, and the integral of e to the power minus sat is e to the power minus s plus divided by minus s plus a, so this will become plus. And the limits here are 0 to infinity, and so this guy will go to 0, and that guy gives us e to the power minus s plus a t divided by s plus a whole square, 0 to infinity, and that turns out to be, what does that turn out to be? 1 over negative sign s plus a whole square. Then let's look at, what are we going to look at? Maybe sine omega t and cos omega t. Let's look at, what are we going to look at? Yeah, sine omega t. And we know by Euler's identity that sine omega t is equal to e to the power j omega t minus e to the power minus j omega t divided by 2j, and therefore the Laplace transform is going to be 1 by 2j times integral from 0 to infinity e to the power j omega t minus e to the power minus j omega t into e to the power minus st dt, and that guy is going to be 1 by 2j times 0 to infinity, oh man, e to the power minus s plus j omega into t minus e to the power minus s minus s. And this guy is going to be 1 by 2j times e to the power minus s plus j omega divided by minus s plus j omega minus e to the power minus s plus j omega times t divided by minus s plus j omega, so that will make this plus s plus j omega, and the limits are 0 to infinity. When you go to infinity, these things, the exponentials go to 0. When you go to 0, the exponentials go to 1, and therefore what you get is 1 by 2j into minus 1 by 2j into 1 over minus s plus j omega plus 1 over s plus j omega, and if you do the necessary math, so this will be s plus j omega minus s plus j omega, the s and the s cancel out, and downstairs we will have j square omega square, which will be minus omega square minus s square, and here we'll have minus 1 by 2j, so that turns out to be 2j and 2j will cancel out. Okay, so this will turn out to be omega by s square plus omega square. We can repeat the same thing for cos omega t. Hang on. So if you look at cos omega t, again it will be 1 by 2 times e to the power minus s plus j omega times t plus e to the power minus s plus j omega t whole thing times dt. The limits are 0 to infinity, and this will turn out to be, by the way, Laplace transform of this is equal to 1 by 2 times hang on, made a mistake here. Minus 0 to infinity, and so what we'll get is half of this will become positive, so 1 over s plus j omega minus 1 over is that right? Is that right? I think I messed up. Did I do it right? Oh well, we'll see. Yeah, this looks okay. This looks okay. So when you go to 0, you'll have the negative limit. Negative limit. This is going to be plus. This is minus. Okay. I think I messed up a sign there. Well, so let me just erase this and do it from scratch again. Hang on. So yeah, this looks good. This is equal to 1 by 2 into okay, so we'll see. Half into, so this guy becomes minus s minus j omega minus s plus j omega divided by j square omega square, which is minus omega square minus s square, and the j omegas cancel out and the minus cancels out, and so we get this is equal. So the Laplace transform of cos omega t turns out to be s over s square plus omega square. So I hope this is a reasonable introduction of introduction to Laplace transform of some common functions, of some commonly encountered functions in controls. So we did this, we did this. We didn't do this, but this should follow from there. We did this, we did this. We didn't do this, but I suppose you can use induction to see that this is actually correct. And we did this, and we did this. So that takes care of that. Now we'll look at Laplace transforms of some time function operators, and let me just look at what we are looking at. So we're going to look at time delay, derivative, nth derivative, integral, and convolution. Okay, so let me just go back. So time delay. So what is time delay? There is a function f of t. You delay it by a dead time theta. So what this means is, if you have f of t, whatever, so you plot the function value with respect to time, and let's say the function is, I don't know, something like this. Then f of t minus theta is going to be delayed by theta, the same function. This is that delay. So this is f of t, this is f of t minus theta, and you can see that by subtracting theta I'm shifting the function rightwards. Yeah, so now we want to find out the Laplace transform of a function that has been delayed by theta time units. So that's going to be equal to integral of f of t minus theta e to the power minus s of t dt, integral 0 to infinity. Put tau is equal to t minus theta, then the integral limits go from, if I put t minus theta to infinity, remains infinity, and then you say f of tau e to the power minus s, instead of t, you say s times tau plus theta dt, and that's equal to or d tau, sorry, and because in Laplace transforms in control systems, system is always at rest at t before t equal to 0. So minus theta to 0, f of tau is 0, and therefore this is equivalent to 0 to infinity. E to the power minus s theta f of tau e to the power minus s tau d tau. With respect to tau, this is a constant, and the integral of this is nothing but the Laplace transform of f. So this is equal to e to the power minus s theta times f of s, the Laplace transform of the function itself. So Laplace transform of a function delayed by theta time units is e to the power minus, well, I like to put it like this, minus theta s times the Laplace transform of the function itself. Now let's look at derivatives. If I look at a derivative, well, let's look at a derivative. Okay, so Laplace transform of df by dt will be equal to integral 0 to infinity df by dt times e to the power minus st dt. This time we'll integrate it by parts. Take this as the first function. Take this, yeah, and take this as the second function. Is that right? No. No. Hang on. I think I made a mistake. Take this as the first function. Second function is easy to integrate. Yes. Okay. So this would be e to the power minus st. I forget the definition of first function and second function, so forget about first function and second function. I'm using integration by parts and I'm confused about which one is first and which one is second. But the easy to integrate function is this guy and the difficult to integrate function is that guy. So e to the power minus st times integral of df by dt minus integral of derivative of e to the power minus st, that is going to be plus s times e to the power minus st times integral of df by dt, which is f dt, and the limits are of course 0 to infinity, and yeah, so this integral will also be f, but then the limits are 0 to infinity, so this guy is going to be e to the power minus st times f 0 to infinity plus if I look at this guy, what is this going to be? S times integral f of t times e to the power minus st dt, and this is nothing but the Laplace transform of the function itself. And here what we get will be when t goes to infinity, e to the power minus st goes to faster than everything else, so this will, as long as f infinity is finite, there is no problem, so this goes to 0. At t equal to 0, this goes to 1, that's f0. So this will be s times f of s minus f0. This is the Laplace transform of df by dt. What is the Laplace transform of the integral of a function? So let's say I want to get the Laplace transform of integral of f of t dt, and let's say integral will be only till current time. So this guy is going to be integral of 0 to t f of t dt, multiply this by e to the power minus st dt 0 to infinity. Now I would like to differentiate, so this will take as the second function, this will take as the first function. Yeah, okay, so is equal to this guy, integral of e to the power minus st will be e to the power minus st divided by minus s times integral of f of t dt 0 to t, and the limits on this guy are from 0 to infinity minus integral of derivative of the integral, which would be f of t times e to the power integral of e to the power minus st, which will be this guy. And let's look at this limit. If I look at this limit, if I put the limit infinity, as long as this integral is finite, e to the power minus st goes to 0 faster than anything else, so the infinity limit is 0. T equal to 0, integral from 0 to 0, that is going to be 0, so this is going to be 0. And therefore what we get is this is going to be equal to 1 by s times f of s. Then we also, so we've looked at dead time, we've looked at differentiation, we've looked at integration. Let's look at convolution. So if you convolve two functions f star g, f and g are functions of time, which by definition is equal to minus infinity to infinity f of tau g of t minus tau d tau. But in controls, f and g are causal, so before t equal to 0, f is going to be 0, and g are going to be, f and g before t equal to 0 are going to be 0. So because of causality, for control theory, due to causality, you say f star g is going to be integral minus infinity to infinity f of tau u of tau, so that when tau is less than 0, f is forced to go to 0. U is the unit step function, and g of t minus tau into u of t minus tau d tau. And you can see that this thing goes to 0 for tau less than 0. So your integrand will go to 0. So minus infinity to 0 you don't have to do, you have to start your integration from t equal to tau equal to 0. This thing will go to 0 for tau greater than t. So therefore your integration limits, you don't have to integrate from minus infinity to infinity, you have to integrate only from 0 to t. So for control purposes, f convolution g by definition for control, for causal realistic cause and effect systems is going to be integral from 0 to t f of tau times g of t minus tau d tau. Now if I want to take the Laplace transform of f convolution g, then basically what I do is 0 to infinity, I'll get a double integral times e to the power minus s of t times the function is 0 to t f of tau g of t minus tau d tau dt. So this guy is integrated first and then you integrate over time. Now let's look at this guy. if I look at this guy, I have my tau axis because I'm integrating with respect to tau, and I'm going to integrate from 0 to tau. So from 0 to t. Now imagine this function. Let us say this is the function. I don't know. This is f tau g t minus tau. What I want to calculate for a given value of t is this area, and everything else should go to 0. So what I can do is I can multiply f tau gt minus tau by u t minus tau, and u t minus tau is going to be like this, 1 and 0 otherwise. So when when tau is greater than t, ut minus tau becomes negative, and therefore it goes to 0. Yeah. So when I multiply this and this guy and this guy, and I take the integral from 0 to infinity of that entity, uh, I'm in good shape. I'm in good shape because instead of 0 to t, I will get 0 to infinity. So that's what I do. I'll say, okay, this guy is 0 to infinity. This integral is over time. And then I do 0 to infinity over tau e to the power minus st times f of tau g of t minus tau into u of t minus tau d tau dt. See, now both the limits are 0 to infinity, so now I can switch the limits and do the time integration first and then do the tau integration. So what I'll do is switch the limits. So this guy is going to be equal to integral over tau 0 to infinity, and f of tau is a constant with respect to t but not tau. So f of tau comes out of the inner integral. Inner integral is over time, and over time over t it goes from 0 to infinity, and I'll take e to the power minus st inside and g of t minus tau into u of t minus tau dt, and then d tau. Okay, let's keep going. Now if you look at this guy, substitute again t minus tau is equal to, I don't know, maybe theta. So let t minus tau is equal to theta, so dt is equal to d theta, and what, and so this becomes integral 0 to infinity, and at t equal to 0 theta is equal to minus tau minus tau to infinity, and from minus tau to 0 it will remain, so it really doesn't matter. So this will become 0 times, what the hell am I doing? This will be e to the power minus s times, instead of t I have tau plus theta, and then I have g theta, u theta, d theta, and this whole thing d tau. So this one was integration along theta, this one is integration along tau, and f of tau remains here. And then you can see what can you see? You can see that this chap is nothing but just put tau plus theta is equal to v. E to the power minus s tau will come out of it. E to the power minus s theta, g theta, u theta is 0 otherwise. So this guy goes to e to the power minus s tau times g of s. And so what I am left with is integration over tau from 0 to infinity e to the power minus s tau times f tau times g of s d tau, and so this guy is nothing but okay, these two guys, is equal to gs times f of s. So what this shows is that Laplace transform of f star g is equal to f of s times g of s. This is the key result that you get. That I wanted to show you. And with this, let me summarize what we have done. For a time delay, if the delay is by theta time units, you simply multiply the Laplace transform of the function itself by e to the power minus theta s. For a derivative, this is what we have, and this can be generalized, and you can prove this by induction. If you have the nth derivative, you have s to the power n times the Laplace transform of the function itself minus a sum of initial conditions. The key point here is that if the initial conditions are 0, which is true when we have a system at rest and the ordinary differential equation is in terms of deviation variables, deviation from the position of rest, from the state of rest. So if you have your ordinary differential equation in terms of deviation variables and the initial condition is a state of rest, state of steady state, then all the initial conditions are 0, and for 0 initial conditions the nth derivative of a function gets replaced by s to the power n. That's the key takeaway. Integral we saw, this is what it was, 1 by s times Laplace transform of the function itself. Convolution just showed you. So that's that. Then we also need to talk about the initial and the final value theorem. And I think what we need to do is take that derivative thing again. So if I was doing the Laplace transform of d by dt of f, then that turned out to be integral of e to the power minus st d by dt of f times dt, and that guy turned out to be f times e to the power minus st 0 to infinity minus integral of e to the power minus st times minus s, so that makes it plus, times f of t times dt. Yeah, and this turns out to be from 0 to infinity, and what we saw was f of e to the power, no, hang on. So f of hang on f of 0 minus plus s times f of s is equal to Laplace transform of df by dt. This is what we got, right? Now the final value theorem states that limit s of f of s, sorry, hang on, limit, if you take the limit of s times f of s, s tending to 0, this will be equal to limit of f of t, t tending to infinity. Initial value theorem states that if you take the limit s times f of s, s tending to infinity, this is going to be f of t, t tending to 0 plus, plus meaning just after you have disturbed the system, just after you have forced the system. For example, just after the step. Now how do we show this? So let me see, it must come from here, s of f of s limit as well, I've gotten stuck. I derived it yesterday, but now I'll have to apply my mind. Oh, let me apply my limited mind. Oh, okay, so this is what this is. Hang on. Okay, this is what we got. Now if I take the limit as s tends to 0, so as s tends to 0, this guy will tend to 1. This guy tends to 1 as s tends to 0. and so you get integral of the derivative of the function, which is the function itself. So function between the limits 0 and infinity should be equal to minus f0 plus s times f of s. So f infinity minus f of 0 should be equal to minus f0 plus s times f of s, and of course we are taking the limit as s is tending to infinity. And therefore this cancels out, so this is what gives us the final value theorem, which is basically saying that if you take s times fs, s times fs and put the limit s tending to infinity, then what you get, the value of that limit, is the final value of the function in the time domain. Initial value theorem, I think what we do is, again, we put s equal to infinity, s tending to infinity here. So if s tends to infinity, this chap goes to 0 as s tends to infinity, and therefore you have 0 equal to minus f0 plus limit s tending to infinity s of f of s. And what that gives is the initial value theorem, which says that if you take s fs and take the limit as s tends to infinity, the value that you get is going to be what? f0, just as things start. Alright, so this is the final value theorem and the initial value theorem. And we've just derived it. So that's that. Now we look at the transfer function. What is the transfer function? Consider a general linear single input single output ordinary differential equation with constant coefficients. That's a linear time invariant. The coefficients are time invariant. Zero initial conditions, and the zero initial conditions are obtained when you got y and u as deviation variables. So the most general form is going to be as stated above, and you can always divide by, say, a naught and get this coefficient to be 1, which is what I like to do. But nevertheless, let's say this is your differential equation. Then if you take the Laplace transform of both the sides, zero initial conditions, well, see, this will go, Laplace transform of this is this. Laplace transform of this is this. Laplace transform of this is this. Yeah. And similarly for the other parts, it's just that the nth derivative is replaced by s to the power n. The mth derivative is replaced by s to the power m. For real systems, for physically realizable systems, n is usually greater than m. The derivative to which the output is, the highest derivative of the output is usually greater than or equal to the highest derivative of the input. Okay, this is, why do we say that? I mean, it's a very simple thing. So let's say you got a cause and effect system, physical system, and let's say we say let's take an ideal derivative, y is equal to d dt of u. Simplest system. So in the Laplace domain we have y of s is equal to s times u of s, and therefore you can see the Here in this case n is equal to 0, m is equal to 1. So n is less than m. Yeah, if n is less than m, now imagine you give a perfect step to the input. If you give a perfect step to the input, its perfect derivative is going to be the Dirac delta. The Dirac delta requires the system to go to infinity and then come back to 0, sweep an area of let's say this is unity, sweep an area of 1 in no time, in 0 time. That's the Dirac delta. No realistic system can give you this. I repeat, no realistic system can give you this, and therefore the simplest dynamically realizable fastest dynamic element is actually the lead lag. And we'll talk about the lead lag a bit later. But in a lead lag, the n and m are 1 each. So you have, for example, alpha dy by dt plus y is equal to beta times du dt plus u. Now if you take Laplace transform of both sides, you'll have alpha times s times y of s plus y of s is equal to beta times s of u of s plus u of s, and so what you get is alpha s plus 1 times y of s, sorry, not to the power, times y of s is equal to beta s plus 1 times u of s. That's what you get, and you can see that both are 1. This is the simplest system physically that is physically realizable. Okay, that's that. So that's why we were saying n must be greater than or equal to m. Now if of this differential governing differential equation, if we Laplace transform both the sides, this is what we get. Collect the ys and us terms together, take ys common, take us common, and then what you get is the transfer function g, which is y of s divided by u of s, because u is the input and y is the output, and there is the ordinary differential equation that relates the output to the input. You get this transfer function. This is called a transfer function. It's a very compact representation of the ODE, and we are saying in block diagram format that the transfer function g, which is a compact representation of this complicated ODE, represents the transfer function g represents the transformation from u to y. Yeah, so this is the block diagram compact representation of the same dynamic system using g, which is a transfer function. The transfer function in itself is a compact ODE representation in the Laplace domain. ODE is in the time domain, transfer function is in the Laplace domain. Well, some common transfer functions. Okay, so let's look at some transfer functions, and then first order lag, you can see Laplace transform both sides, so tau times y of s plus y of s is equal to k times u of s, and therefore you get g is equal to y of output by input is equal to tau s, sorry, k by tau s plus 1. D by dt is replaced by s. Yeah, so that's pretty straightforward. Uh, okay, this is also pretty straightforward. You have u. Okay, so you have the input u. It is delayed by time units theta. So there's a delay of theta time units. This delayed thing goes into an ODE, you know, goes into a transfer function of the type k by tau s plus 1, and then you get out y. This delay, this is u, delayed by theta, and so this guy must be e to the power minus theta s, because u of Laplace transform of u of t minus theta is equal to Laplace transform of u times e to the power minus theta s. This we have derived earlier, and therefore the overall transfer function from here to here is k by tau s plus 1 times e to the power minus theta s. This is the first order plus delay, plus time delay transfer function, which we will see ये क्या हुआ यार, which we will see quite a bit. Alright, two equal lags, that means, well, that means exactly this. So that's essentially two lags in series, and with maybe a gain. So you have 1 by tau s plus 1, you got 1 by tau s plus 1, that's u and that's y, and so the overall transfer function that you get is this, and the differential equation corresponding to this guy is this guy. It's easier to work from here to here rather than from here to here. Yeah, but so I'll go this way, you guys can figure out the forward way. Different lags, so that means the first lag is 1 by tau 1 s plus 1, second lag is 1 by different time constant 1 by tau 2 s plus 1, and multiplied by again, this is u, this is y, and you can see that the transfer function turns out to be this, and if you just expand this transfer function, you'll get tau 1 tau 2 s square plus tau 1 plus tau 2 s plus 1. So tau 1 tau 2 second derivative corresponding to s square plus tau 1 plus tau 2 s corresponding to the first derivative plus y is equal to ku. That's the differential equation that you get. So much easier to work the other way. N equal lags, this is what you get. N unequal lags, oh, I'm sorry, this should be a small I. General second order ordinary differential equation, transfer function, PI controller. This is interesting. Let's look at the PI controller. So if you take the Laplace transform of both sides, you will get US is equal to Kc times E of S plus 1 by tau I times integral of the error, so that will be 1 by S times E of S. So U of S by E of S is going to be Kc times 1 plus 1 by tau I S, and that's going to be Kc times tau I S plus 1 divided by tau I S. Is this physically realizable? Yes, because the order of the numerator is 1 and the order of the denominator is also 1. So yes, it is physically realizable. So this is a PI controller. and you can have more complicated transfer functions. The bottom line is it is so much easier to work with transfer functions and algebraically manipulate the expressions in S rather than work with all these complicated differential equations. That's why Laplace transforms. So here's an exercise. We just derived the PI controller. Derive the transfer function for a PID controller. And this is what we look at, and of course this is in terms of deviation variables, changes from the initial steady state. Once you have derived the transfer function, is the transfer function physically realizable? Justify why not? Okay, so that's just a very simple exercise for this module or sub-module. With this, let me summarize what we have done in this lecture. We've looked at the Laplace transform, which is defined as shown on your screen. It converts a linear time invariant ordinary differential equation into a much easier to manipulate algebraic equation. We have derived Laplace transforms of some commonly encountered time functions. We've also looked at the transfer function as a very compact Laplace domain representation of the linear time invariant ordinary differential equation. We've looked at some commonly encountered transfer functions. That's what we've done in this lecture. With this, we come to the end of this lecture. Thank you very much for your attention. Hope to see you next time. Thank you and goodbye.